On functional programming, technical reasons to adapt. We're going to talk about some of the reasons why we should consider programming in more of a functional style. So most of us, especially programming in Java, have been programming in an imperative style of coding, and we want to really look at some of the reasons to really adapt a style that's been around for quite a while, but certainly fairly new to Java. So we'll talk about some of the reasons, look at some examples along the way. The best time to ask questions or make comments is whenever you have it. So please don't wait till the end. Anytime is a great time. Just draw my attention, speak up, and we can talk about it. So the first question I want to start out is, why should we really consider something like functional programming? What are some of the reasons to program in functional style? Well, there are certain things that's changed over the past about 15 to 20 years. And one of them is the growth of computer applications. If you look around what's happened over the past decade plus, the organizations, companies have gone from making their employees available to the customers to making their applications available to customers. I remember physically walking into a bank where I had to open an account, or walk into a bank to perform a transaction like depositing money or withdrawing money. I haven't walked into a bank in quite a while now. So rather than having employees of the bank that I talk to, now I interact directly with applications the bank provide. When you have applications that are provided to customers, the order of magnitude of users increases phenomenally. Second thing is, when you have employees accessing your application, employees are often captive users. They can't really do a whole lot other than use the application you provide. But when your users are not your employees, but your customers, they are not going to be as patient with you or tolerant with you as your employees are. So applications have to perform really well. They have to be responsive. They have to be able to really support and scale as well. Well, another thing is, if you really think about what we do on a daily basis, we pretty much are dealing with complexity. So most of the day, what do you normally do when you get to work? You fight complexity. But there are two kinds of complexities that you have to work with. One is inherent complexity, where inherent complexity is the complexity that comes from the problem domain, and the other complexity that you have to deal with is called the accidental complexity. Now, inherent complexity, you can't do much about it. That is dependent on the nature of the problem, the application you are building, and you can't really get rid of the inherent complexity. However, accidental complexity often comes from the problem solution domain. So depending on what solution you are using, those solutions may pose a few accidental complexity. Now, what do you do when you face accidental complexity? You bring other solutions to solve that problem. And what do those other solutions do? Bring complexity with them, and now we spiral into this vicious cycle where we are simply fighting these accidental complexity, and that becomes really hard to manage the code after a while. Now, object-oriented programming has been fairly effective for what we do, but there are some rough edges around object-oriented programming as well. One of the things that object-oriented programming doesn't deal with really well is the so-called mutable state. And when you have shared mutability, it becomes really hard to deal with this over time, and that becomes enormously complex as well. And finally, of course, the world around us has changed in another way, not just in terms of how businesses operate, but also in terms of what kind of computer power we have on our hand. Most of us now carry around computers which are a lot more powerful than computers that filled big rooms like this only 20, 30 years ago. So we have enormous computing power on our hands. We carry multi-core processors, and with those multi-core processors, we have more capability. Multi-threading definitely becomes available, but the question is the software solutions we have capable of really making use of those capabilities of hardware? And the short answer is it's not been, because imperative style really makes it really hard to make use of multi-core processors to a great extent. So with all that said, let's talk about mutable state. One of the reasons I want to talk about mutable state is, in the very first thing you will see when it comes to functional programming is, functional programming will tell you that we're not going to allow mutability. Now, there are other reasons and other benefits of functional programming. I'll talk about those later on. But let's start with the very first thing we normally see. In functional programming, we don't deal with mutability. But why should we really be so upset about mutability? Why should we not provide mutability so much? And the reason simply is there are quite a few challenges when it comes to mutability. The first thing is error prone. The more mutability you have in your code, the more error prone your code actually becomes. Now think about this for a second. Now let's say you have a function in Java, and then let's say the function is called foo, and I have a variable a coming in here, and I want to output the variable value a. Well, I could call this, and clearly there's not a big deal. We are able to run this very nicely. But what if I were to say a equals 22 right here, and try to change the value of a? Well, clearly in this case you can see Java does not complain. It kind of keeps quiet. Now, if you read effective Java, what does effective Java say? Effective Java says, hey, do not mutate your input parameter. In fact, if you follow effective Java, you would probably say final up here in the parameter list. Now, why does effective Java say consider things as much as possible as final? And the reason is fairly simple. When your code takes a parameter and modifies it, we normally end up really having trouble with such code. I had a programmer come to me and he said, I wrote this function, and for the life of me, I cannot figure out why this function doesn't work. And I quickly look at his code, and then I tell him, if you send this input, it should produce this output. He says, I know, right? But it doesn't. So we both are looking at the code like we are idiots, going over it several times. After about 10 minutes, I said, wait, on line number 7, did you really mean to change the input parameter? And the minute I said this, he looks at it for a second and he says, you know what, I'm stupid, and he walks away. Because he didn't realize that he's actually changing an input parameter. And I'm sure you have seen your share of this when our mind doesn't quite think through all the mutability that goes through in the code. And as a result, we often end up having errors in code. So the more mutability you have in code, the more error you have in code as well. In fact, from a good language point of view, we want to do the right things when it comes to languages themselves. So here is an example in Scala for a minute. Let's say we have a function called foo, very similar to what we did. I've defined the variable as integer right here. And I'm going to, within this function, let's say, go ahead and print out the value of a. I'm going to call the function foo like we did in the Java side. We are calling it here in Scala. But within Scala, I'm going to say a equals 22, just like I did in the Java case. But when I run this code, notice Scala immediately complains to me that I cannot modify the variable a because Scala by default treats the parameter as if it is final. So Scala says, if you are passing a parameter, I am not going to let you change it. The other day, somebody asked me, they said, oh, this is really nice, I like it, but is there a way to really change this so that I can actually modify the parameter? And the answer is yes, go back and program in Java, right? So the point really is, the language is very highly opinionated. It says, no, this is the right thing to do, and I'm not going to let you do it otherwise. So in other words, when you have parameters coming in, modifying the parameter is such a terrible idea. The number of use cases where you want to modify the parameter is equal to 0. So there is no reason actually to do this in a good programming practice, and the languages can promote it. In fact, you can go to the next extent. If you think about defaults, or what kind of defaults does a language provide for you? Well, when a language provides defaults, you want the language to fall on what I would like to call as a safe default. A safe default is where the automatic behavior is something very safe and very comfortable from the programmer point of view. So in the case of Java, unfortunately, a lot of safe defaults are really not the best defaults you could rely upon. Because, of course, there's legacy. Java came from a very different background and mindset than what we want it to be today. So by default, variables in Java are mutable. Whereas in functional programming, variables are immutable and from the get-go. Well, what does Scala do? Well, Scala wants you to make a very clear distinction when you're defining variables. So I'm going to say max equals 100 right here. I'm going to print the value of max right here. And you can see that I was able to print the value. Well, before I print the value one more time, I want to say, in this case, max equals, let's say, 4. Well, I get a compilation error saying I cannot modify the value. Why? Because it's declared as a val. So val is an immutable variable in the language, and you cannot modify it. Now, unfortunately, though, Scala is not a pure functional programming language. Scala is actually a hybrid functional programming language. So what that means is, in Scala, you can actually define a var. And when you define a var, you can see Scala does not complain anymore. So what's the difference between val and var? Var in Scala is called the keyword of shame. So if you ever use this, you cannot make eye contact with your colleagues anymore. You walk looking down on the floor the rest of the day, and they look at you and say, you made a variable mutable, didn't you, right? So you kind of immediately figure out this is not something you want to do. So you don't want to really use mutability. And the beauty of this is the following. When I wrote my book on concurrency on the JVM, somebody tweeted saying, oh my gosh, I looked at Venkat's book. He's got 350 uses of the word final. I tweeted back saying, aha, but you don't know where I still forgot to put final. That was the lowest point of writing that book, because I had to go through every line of code and figure out where I forgot to put final. So how do you find where you have the word final? That's very easy. You can just grep for it. But the question is, how do you find out where you forgot to put final? There's no easy grep for that. You have to rely on other tools to do this. Whereas in the case of Scala, you can do a quick grep on var and try to look at the code and see if you have to refactor it. So that's a very safe default to really fall back on is a val, and you can easily find that for you if you want to. So it's error prone. The code is hard to reason. I'm sure you have seen your share of this. You're looking through a piece of code where the code is changing several variables through it, and you have had it. You cannot figure out what the code is doing. So you sit in a quiet room, and you take a piece of paper, and you put the variable names down, and you're going through the code and keeping the variable values, and you're striking them and changing it. Ever done that before? Right? And this all works fine until somebody asks you a question, and it's completely lost. You have to start over again. That's an example of a code that's very hard to reason. Or somebody asks you, how does this code work? And you're struggling to explain how the code is working through all these state change, and it becomes extremely difficult to really understand it. Here's a way to think about it. How many of you in this room are really good at juggling? How many of you can juggle? Not one person, right? And while you're juggling, can you sing a song as well? He didn't try it. He doesn't dare to even try it. Or what about bicycling while you're juggling? Did you try that either? Right. So when you juggle, do you even think of anything else? It draws all your attention, isn't it? So there's a reason why there's only one person brave enough to attempt juggling here, because rest of us know that juggling sucks. But actually, let me ask you again, how many of you juggled in this room? And every one of you should raise your hand, because that's called programming, right? Because every day we juggle through variables, and we're all this brave people. And that's why when you code, you are so focused. We all do this, right? Programmers are considered to be weird for a reason. And of course, when you code, what do? You are into it. You built this mental model. You know what I'm talking about, right? This mental model, you have these objects in memory, and you're sitting there and coding, and somebody asks you a question, they interrupt you. You kind of stare at them, and they're like, are you okay? It's like, no, I'm not okay. Look what you did. And they just disrupted mental model. You know what I'm talking about, right? So I have a wonderful wife, and she always would look at me and say, why are you so weird? Why can't I talk to you while you work? And finally, this was the best money I ever paid. I went to this movie called The Social Network. You probably have seen the movie. So we are in the middle of the movie when my wife suddenly screams, I get it. And I'm like, what happened? Well, there was a scene where these guys are coding away with their headset, and one of the guys walks in and is about to ask a question. He said, don't talk to them. They're wired. And my wife is like, I get it. I understand why you are like this. And this was the moment, right? It was worth paying for this movie. A few weeks later, I was at home working away. One of my kids came to me and said, wanted to have a question. And my wife is like, don't talk to daddy now. He's wired. I'm like, this is awesome, right? So the point really is, there's a reason why we are wired. Because we built all this mental model in our minds, and when somebody asks you a question, it completely disrupts the flow, and we don't really like it. Well, it becomes really hard to understand and work with the code. The more mutability we have, and becomes hard to reason as time goes on. Then comes along a concurrency. Now, let's say for a minute you wrote a piece of code, and the code actually is working, and somebody comes to you and says, let's use multi-threading on this piece of code. Now you're not smiling anymore, right? You're like, where's the nearest door out? Because what happens when you start using threads in code? You probably remember the last job you were on, and everybody smiled at each other in the morning when they came to work. You shake hands with people, and you had a sequential code. People could understand the code. Everything was really nice. And one day they said, we got to use multi-threading. So what did you do? You started changing the code. Now you got threads everywhere. But threads never come alone. What do they come with? They come with locks everywhere that you see them, right? And now you got locks everywhere in the code. And what did the code do? The code suddenly turned into a monster. And then you fear getting to work every day. And the minute you get to work, what do? You start debugging the stupid code. And you're sitting there and debugging until late in the night. And you leave the pizza next to the keyboard and walk away home because you're so tired to even collect the garbage. And the next morning you come, wipe things out, and you start debugging again. Remember that? Well, why does debugging become so difficult in multi-threaded code? Well, because we are talking about this mutable state. Again, the juggling, right? All these variables are being juggled. We can't really handle them so easily. Life becomes extremely miserable. And so what did you do eventually? While you were working on this project where every corner you turned there was bug, and you finally had it. So in the middle of your debugging session, you applied for this other job. That's defined as concurrency, right? So you're like, never mind, I don't want to do this anymore because this is horrible. So with all that said, we can talk about what functional programming can do for us. Well, what is old again? Old is new again. Well, let's talk about this for a second. Do you remember the year when object-oriented programming was introduced? Don't worry about being wrong. Don't worry about being right. But what year do you think it was introduced? What year was introduced? Anybody remembers? What was that? 60s? Well, actually, you are correct. It was actually 1967 when two Norwegians, Dahl and Nygaard, introduced object-oriented programming. Well, do you remember the year when object-oriented programming became mainstream? Like nobody even questioned whether this is the right thing to do. They blindly started using it. What year was that? Yeah, 90s. Okay, let's take that. You are absolutely right. So 1990, let's say. Well, what was that? A good 23 years. Can you imagine this? If object-oriented programming was a human, it had a terrible childhood. Nobody wanted to talk to it. Until it was 23, they said, hey, handsome, do you want to hang out, right? So it took 23 years for this to really become so mainstream. Well, here's another question. When do you think the concepts behind a functional programming, not necessarily functional programming itself, but things like lambda expressions or lambda calculus, do you remember, does anybody can guess when this was introduced into the world? I heard 50. What else? 60s? 70? This is like auction. Do you see this? We're throwing numbers at each other. How about 1929? Yeah, okay, what? Everybody here knows of Alan Turing, right? You know who Alan Turing is? This was Alan Turing's professor, Alonzo Church, who introduced the concept of lambda calculus back in 1929. Here's the last question for you. What year do you think functional programming became mainstream? Okay, that was a trick question. Not yet. He's nodding the head. It's like, I'm still awake. It's not true. Yeah, it's not yet. So a good 80 plus years later, we are just getting excited about these concepts. So when people come to me and say, in computer field, things change really fast, I look at them and say, what are you smoking? It's taken us decades for us to change what we do. We don't really move as fast as we think we do. It is taking forever. So this is a concept that's been around for a very long time. And so what happened in this case? Well, one of the things that functional programming really emphasizes is assignmentless programming. If you look at languages like Haskell, probably Haskell is one of the most purely functional programming languages, and these languages don't provide assignment. And you may look at this and say, that's crazy stuff. How could you possibly program in a language where there is no mutability at all? We can't even imagine writing code in a language where you cannot change a variable once you create it. But before we go that route, I want to draw a similarity to this with something else that we have gone through in the past so we can kind of relate this to something that we are more comfortable with. Well, think about structured programming for just a minute. So structured programming, what is that? Well, remember, one of the things about structured programming is good old Edgar Dijkstra said, go-tos are considered to be harmful. He wrote a phenomenal paper where he told the world we shouldn't use go-tos. We should not really jump around in the program. So he said, no go-to for you. Well, why did he say no go-to? Well, because when you have a go-to statement in the code, what does the code really do? You can select a particular statement and arbitrarily jump to that statement from anywhere you are in execution. What does that mean in a world like a real world we are in? Well, there is 2 doors for this room, and it's perfectly acceptable for one of these doors to open and for somebody to come in. You're not going to have a problem with it. But you will freak out if somebody suddenly appears next to you, right? And go-to is kind of like that. The code suddenly bolts and says, I'm here. It's like, where are you? Who are you? Where do you come from, right? So there's no context being carried with it, and it becomes a spaghetti code for us to handle. So no more go-tos for you. Great, that's a great idea. But let's entertain a thought for a minute. Suppose I were to say blah here in Java code, and I'm going to run this Java code. Notice very carefully what Java is telling. Java says blah is not a statement. Just keep that in mind, not a statement. On the other hand, if I were to say go-to on the other hand, notice the error is different. It didn't say not a statement. It says illegal start of expression. So Java is kind of hinting, go-to is okay, but I dare you to use it. So in other words, it's a valid keyword in the language, but it's a forbidden keyword. We are not supposed to use it. Well, it kind of gives us a little bit of a clue of something going on here, but let's come back to that. I'm going to say for int I equal to 0, I less than 10, I plus plus. And in this case, let's simply say if I is greater than 5, I want to output the value I. Very simple code, as you can see, nothing really exceptional. But let's quickly take a look at what this code actually has under the hood for us. So Java P minus C is an option on my machine already. And I'm going to take a look at the sample class for a minute. And guess what we see at the bytecode level? Well, notice we have that wonderful go-to sitting here at the bytecode level. So you may wonder and say, wait a minute, didn't we agree we won't use go-to? Yes, we did. Then why is there go-to? Well, it's kind of like matches. You have matches at home, right? You have to, live and cook and stuff like that. But I hope you don't do this. You don't go to the children and say, children, I'm going to go take shower. So while I'm showering, here's some matches for you to play with. I hope you don't do that, right? So while there are matches in the house, you don't give matches to children. You let adults use matches. Exactly the case in point. So the point is, we don't get to use go-to, but the adults can use go-to, and they can do it very carefully, absolutely. So in other words, structured programming discourages the use of go-to. That doesn't mean there's no go-to. It's just that we don't use go-to in our code. In a very similar way, in functional programming, we don't use assignment. It doesn't mean there's no assignment at all. In fact, if you look at what Java does, Java assumes that lambdas are pure. Java assumes that functions are pure when it comes to functional style. But if you look into the JDK, you're going to see places where they do mutation. However, you don't look at that and say, look, they use mutability, so I can in my code. That's a very flawed logic. And the reason is, if you do mutability in code, reasoning the code becomes your problem. Understanding the code becomes your problem. Concurrency becomes your problem. And explaining the code becomes your problem. And you can keep going with all the problems of mutability. If they do mutability, concurrency becomes their problem. Understanding the code becomes their problem. Every one of them becomes their problem. In life, you always want to make things other people's problem, right? So you don't have to deal with mutability, then it's not your concern. You rely upon these libraries and be done with it. That becomes a lot easier to work with. So the idea really in this case is you don't want to really use assignment. That's one of the very first things that functional programming tells us is we're not going to mutate variables around us. So we deal with immutable state. So what does it mean by immutable state? Well, what it means by immutable state really is that you are not going to go around and change the state of an object, but instead what you're going to do is you're going to transform objects from one state to another. Now think about this for a minute. What does it mean by transforming objects? Well, you're not going to make a change to an object. Instead, you're going to make a copy of the object. Now, at the very first thought, hey, this is great. I'm not mutating an object. I'm going to make a copy. So original doesn't change. Life is good so far. But that could also mean another problem. What about overhead of copying the object over and over and over? Well, that could become a problem if we start copying objects repeatedly. How can we make that a little more efficient? Well, this is where what are called persistent data structures come in. So what we can do instead is, rather than copying objects over and over, we can make it a lot more efficient. Now, how can we make this a little bit more efficient? Let's imagine for a minute that I have a list of objects. And imagine the list, of course, is immutable. You cannot modify the list. Well, great, I cannot modify the list. So here is my initial list. Let's say list has element 1. Let's say element 1, and then it's got element 2, and then next to it, it's got element 3, let's say. So there are these 3 elements in this list. Well, given this list, I'm going to make this list completely immutable. I cannot change the list. Well, that's great. Because I cannot change the list, if I want a new list with one additional element in it, how do I really make that happen? Well, one naive way to do this would be to make a copy of this entire list over here and then try to add an element to the beginning of the list. But unfortunately, though, this approach would result in copying of the collection, and that you quickly would become an order of n operation, which is not going to be very fun. Bigger the value of n, the slower this is going to become. Nobody is going to be excited doing this. But thankfully, we don't have to do that. Well, the beauty of this is, remember, this list is absolutely immutable. So when something is immutable, there has got one benefit already. What is immutable is extremely safe to share. In fact, remember, string is immutable in Java, but internally we have interning and we can share the string values. So that's exactly what we can do here. Because this list is immutable, if I have a little reference coming into this particular location in the code, let's say we have a little reference coming into E1, you can ask how many elements this collection has. Well, the answer is it's got 3 elements. But I can quickly come down here and quietly I can add an element 0 to this collection, and we can easily say this element 0 is going to be the first element that's going to completely share all these values in here. Well, because these are immutable, you can readily share them. There is no risk in sharing them. So what is the cost of this operation? It's order of 1, because all you had to do was simply add an element to the beginning and say you are the first element to this collection, but the rest of the collection is exactly the same as it was before. So the cost is really a constant time operation to take this collection and put another element to the front of it without ever changing the collection. Well, this is about a list where you're adding element to the front. And you know what a list is? If you add elements to the front all the time and remove elements from the front all the time, we call them as stacks. And so stacks are very common data structures we use in algorithms. But what if I don't want to add to the beginning and remove from the beginning all the time? What would I then do? Well, there are other data structures. For example, one of them is called tries. And tries is a data structure that is called a persistent data structure. This was created by Phil Bagwell, but languages like Scala and Clojure use this quite effectively. And in the case of tries, you use a very large branching factor. So you arrange things in a tree-like structure where every node may contain 32 or more children, and you can have all these nodes that will hold these children, but when it comes time to change it, because it's immutable, you can selectively make copies of elements. Well, when you have a hierarchy of size 4, with 32 children for each element, you can have more than 1 million elements within just a collection of size 4 depth. And so to make a copy, you can still make an effectively constant copy of a very large data structure. I ran some numbers of this. I took the tries from Scala, but I used it in Java code, and I found that for 100,000 elements, I was able to make copies of this collection in under 33 nanoseconds. So you can do fairly, really good performance as well with tries, and you can get really good performance. There are techniques like that that you can actually begin to use, where you can treat immutable state and get performance as well at the same time. Well, the next thing that you get out of this is functions which are considered to be first-class citizens. And so you can not only pass objects to functions, we can start passing functions to functions as well. And this leads to what are called higher-order functions. Let's understand what that means to have higher-order functions. Well, before we talk about higher-order functions, if some functions are higher order, what are other functions? Well, those functions are called as normal functions. So what is a normal function? A normal function is a function which generally takes objects or primitives, and also you could say takes objects or primitives, and also or may return objects or primitives. So in other words, normal functions normally take objects or primitives and then return objects or primitives. We've been using these for quite a while. Well, we are going to use what are called higher order functions, and higher order functions basically are functions that can take not just these, but may also take functions or return functions as well. So you can start passing functions to functions rather than just returning objects alone from functions. You can do quite a few interesting things with it. Let's understand an example of what this feels like to be able to do in the context of what we are very familiar with in the Java code itself. So in this case, I'm going to say, let's say we are going to create a thread, and I'm going to say thread equals new thread, and I'm going to say thread.start right here, and then I'm going to say, in this case, in main for a minute. Well, that's a main thread. That's what I have so far. But what about this other thread we are starting? Well, I'm going to say new runnable, and in this case, I'm going to type public void run. And within the run method, of course, I'm going to say in another thread. Well, we can clearly see that this code is running in another thread right here, whatever the thread we created. And you can see the sequence in which it runs kind of is non-deterministic. So that's a code in another thread. But what did we just do? What we did here is we created this little guy here. Anybody remembers what this is called? That's right, anonymous inner class. Anybody here who is excited about anonymous inner class? Do you wake up in the morning and say, yes, I'm going to go to work today and write more anonymous inner classes? Do you get excited about that kind of stuff? No, right? In fact, if that's what you remember when you wake up, you probably call the boss and say, I'm feeling very sick today, I'm not coming to work, right? So it feels that way. Nobody likes anonymous inner classes. I call these missed opportunity, because rather than creating anonymous inner classes, they could have created lambdas back then and would have had lambdas for quite a while. Well, thankfully, we don't have to do that. So notice what I'm going to do. I'm going to take this code right here. I'm going to rewrite this time. But rather than using anonymous inner class, I'm going to take this part and remove the noise in this code. And I'm going to replace this with just a lambda expression or just an anonymous function. So we can see in this case, I transformed the code from where we were passing anonymous inner class to just a lambda expression. So what are we really doing in the line that we have here highlighted? Well, we are simply passing a function to this constructor. So this constructor being one that was accepting an object a minute ago is now saying I can accept a function as a parameter. So that constructor just elevated itself as a higher order function. So a higher order function is a function to which you can either pass a function as a parameter or you can return a function as a result from the function. Those are called higher order functions. So now rather than composing your system purely using these objects, you can start composing them with these functions as well, and you can start passing functions to functions, and this gives you a better tool on your hand to start working with, and that's one of the very first things that functional programming provides. So we talked about two things so far. The first is immutability. You don't mutate anything in your code. Once you create an object, you create the object and simply use it, and you transform objects rather than mutating objects. That's the first thing we talked about. The second thing we are saying is, in addition to practicing immutability, we're going to start programming with higher order functions. And what that means by higher order functions is we can pass functions to functions and or return function from functions as well. But these functions are not going to mutate either, because we agreed we're not going to mutate stuff. And now we are formulating this with these functions together to build a system. Now the third thing we're going to do here is we're going to go one step further. Functions are going to be pure functions. So what is a pure function? A pure function is a function that does not have any side effects. Now let's think about this. What does it mean by a function does not have side effects? Well, when a function does not have any side effects, so we first said immutability. Now we said immutability leads to pure functions, and that's the next step. But what is a pure function? That's the next question to ask. Well, a pure function has no side effects. Now, what does it mean it doesn't have any side effects? Let's address this with a little example here. Suppose I have a function, and all that this function is doing is taking some parameters, doing some work, and returning a result to you. Well, it doesn't change anything. Well, there are some really good things about such a function. When a function doesn't change anything, all it does is it takes some input, produces a result. There are some really good things you can do with it. For example, you can call that function any number of times, and as long as the input is exactly the same, the output will be absolutely the same all the time. That's one benefit you get. These are called idempotency. Idempotent functions are functions that give you the same result no matter how many times you call it with the same input. Now, what happens when a function is idempotent? Well, the very first thing is testing such a function becomes extremely simple. Now, let me define what a pure function is. A pure function has two things to it, and I want to emphasize that there are two things we need to really honor. The first thing is the function does not change anything. That is the very first thing, and probably most of us said, yep, that's exactly what I expect of a pure function. A function doesn't change anything. So in other words, you call this function, while this function is running, it doesn't change some global variables or private variables or fields and then quietly walk away. What happens when a function starts changing stuff everywhere? You become really wary of calling this function. You call the function, and when you're trying to test, what do? You call this function and say, oh my gosh, I got to make sure all these other state externally have changed properly also. That's one problem you're going to deal with. But there's another problem, right? If this function is going to change a global state, what do you have to do if you're in a multi-threading situation? You got to lock that state first, and then you got to call this function. Because while this function is running, you don't want that state to be changing, because bad things happen when things change at the same time. So programming becomes more complex when a function begins to change stuff. But that's not enough for a function to be pure. You cannot say, I wrote a function, I'm not changing anything, so I am good. Time out, that's not actually true. It's not only enough that you don't change anything, it is also true that the function does not depend on anything that changes. So this is also very important for a function to be pure. So if you want really a catchy phrase to remember this, I will call this as do no evil and see no evil, right? It's both. So you cannot say, I am not changing anything, so I'm good. No, it's not true. You're not doing anything, but you're also not relying on something that's changing. I'll give you an example of this. I have a piece of code. I'm the only developer on this piece of code. But I have this habit of running all the tests before I actually change the code. So I would work on this code once in a few weeks. I'll take the code, run all the tests are passing, and I'll happily start coding away, and I'll make sure all the tests pass, and I would check in the code. Well, I took a very long flight. This was about a 20-hour flight, and after the very long flight, I landed in a completely different time zone. It was 2 a.m. I checked into the hotel, and after I checked into the hotel, I thought to myself, what do I want to do? And I thought, this is a great time to write some code. So I took my code, and I said, I'm going to write code, but remember, I always run my test before I run the code, so I ran all my tests. And I was pretty shocked because a few of my tests actually failed. And I thought to myself, what do airlines do to code these days? All I did was I flew, and now the code is not working. And I started digging into why the code is not working. And what I found was something a little weird. I had some functions that were actually checking for a certain task that I had started in my code. And so some of my tests said, start a task simulating 3 hours ago, and make sure the task completed on the same day. Well, this is a bit of a good news to hear. This tells you that I actually never work past midnight. Either I work late into the night or fairly early in the morning, but I'm not a big person coding between 12 a.m. and 4 a.m. I normally don't code. Well, here I was at 2 a.m., and a task I simulated to start 3 hours earlier finished at 2 a.m., and guess what? The code says that's not the same day, and the test was beginning to fail. And I realized what I did wrong, and what was about to fix it when I realized why the code actually was failing. And the reason the code was failing was the code was actually depending on the time. And guess what? One thing about time keeps changing. So if you are running a piece of code and the code says, I want to know what the time is, well, that's where we get all the timing problems that we have to deal with. But instead of that, if you give the time as a parameter to the function and as a constant, then the code is not going to fail based on the current time. And that's exactly what I did. I refactored the code to send in the time value rather than the code reading the time. So if you want a function to be pure, you need to make sure that both the conditions that we listed here are true. You don't change anything outside, and you don't depend on anything that changes as well. Well, this leads to quite a few interesting benefits that we can get. So we said if a function is pure, it has no side effect. Well, let's now talk about no side effect. Now, what is the benefits of having no side effects? Well, the first benefit you get out of this is easier to test. And the function is idempotent, I mentioned that. And it also is easier to understand. And that's one other thing you're going to see with this. But there is more benefits to this particular feature. Well, there is something else we can do when a function becomes pure. Let's say for a minute, you are calling a function, let's say. So I'm going to call a function f1. And let's say f1 does a plus b. I got a function f2. And f2 does, let's say, a minus b. And of course, imagine a and b are, final. Let's take that for a minute. So a and b are final. So my code says I'm going to call f1, then I'm going to call f2. So it's going to call these two functions in this order. Now, my compiler says, you know what? I don't want to call these two functions in that order. I'm going to do something a little different. So imagine for a minute that I've got these two functions, a green function and a red function. And my compiler says, I'm going to run the green function first, and then I'm going to run the red function afterwards. So it runs in this sequence. But imagine that function, the green function and the red function, both are absolutely pure. What does that mean? They don't change anything, and they don't depend on anything that changes. So here's my question to you. Can the compiler say, oh, look what I found. It's a lot more efficient to run the red function first and then run the green function. So the compiler, without telling me anything, decides to run the red function and then run the green function. Are we in trouble, or is it okay? It's okay, absolutely, right? No problem. How so? Because the two functions are pure. But what if I tell you that the functions may actually change something quietly outside? and now you're telling the compiler is going to reorder, what would you say? It's in trouble, right? So the compiler says, I will not even touch this code with a 9-foot pole. And what does the compiler say? The compiler says, this code is very smelly. And it walks away and says, no optimization for you, right? On the other hand, if the function is pure, it can do this, or it can do this, or even better, the compiler can look over and say, look what I found. There are multiple cores. We know this as a JIT compiler. And it can even schedule them concurrently like this at the same time. So I'll give you the most stupid example of what I mean here. Let's say, think about this for a minute. And when I mention you, you know I'm talking about you. There are some people in this room, and you know who I'm talking about when I mention you. You put on your shirt first this morning before you put on your pants. There are other people in this room, and you also know when I talk about you. You put on your pants first this morning before you put on your shirt. Don't reveal this to anybody. But I got some good news for you. I looked around the room, and everybody here is decent. They got pants on, and they got their shirts on. So guess what? Whether you are those people who put on your shirt first, or whether you're the people who put on your pants first, I got good news for you. Nobody cares, right? Nobody knows. When they look at you, they don't look at you and say, did he put on his shirt first or a pant first, right? I don't care. And in fact, tomorrow, you can feel liberated in the morning. When you go back to dress up in the morning, you can pause for a minute and say, I remember what Venkat said. For a change today, I'm going to try the opposite. And nobody would ever know, I guarantee it, right? So the point is, it doesn't matter to us whether you put your pants on first or your shirts on first. We only care about one thing. You got both of them on, right? And the point really is, it doesn't matter. The only time this becomes a problem is, occasionally one of my kids will run into my closet. And then they would scream and run and say, Mommy, Mommy, Daddy is not dressed. And usually my wife is, why did you go into Daddy's closet anyways, right? So that solves the problem. So in fact, compilers rely on this extensively. Compiler says, as long as the external view of the world is the same, we can optimize the code any way we want to, as long as we preserve the output. So compilers can optimize quite effectively. And what do we call this one? That feature I just explained is called as referential. So this is called referential transparency. So the referential transparency means you can reorder functions. You can even replace functions with values of the functions if you wanted to. But the benefit doesn't stop there. You can go a little further with this. Let's think about one other example of this and how we can benefit from this. Could I ask one of you to help me here with a little problem? Can you help me here, sir? Yeah, you can stay there, but you can help me from there. Are you ready? I'm going to ask you some really tough math problems. Are you ready for it? What's your name? Sergey, are you ready? All right, he says yes. This is going to be really hard. What is 2 plus 5? He was really quick. I've not seen such a fast processor so far. It's amazing. He said 7. He didn't need warm-up time. Did you see that? This is awesome. I want to know how many cores you've got. Okay, but let's try this one more time. What is 2 plus 7? I'm sorry, 2 plus 5? So are you going to change your answer if I ask you again? No, right? So it doesn't matter how many times I ask him, he's going to say exactly the same answer. Why? Because we know a couple of things. He knows that 2 is a constant. He knows that 5 is a constant. But he also knows one more thing. What is that? Plus is pure, right? Plus is a pure operation. If somebody told you, when you call plus, it will sneak around and change stuff. Plus will not be your friend anymore, right? You are going to hate plus from now on. You will never teach this in kindergarten anymore, right? You will say, children, stay away from plus. It's a bad function, right? Well, plus is a pure function. It's safe to give it to children to play with, right? It doesn't hurt anybody. So it doesn't change anything. It's a pure function. Well, sir, I'm going to ask you for one more help, if you're ready. All right, he's good. 121 plus 325 equals 446, did you say? Is that correct? All right, you had help over there saying you're right. So 121 plus 326 is 446. Let's try this one more time. Are you ready? What is 121 plus 325? Did you notice the difference? What was the difference? He was wicked fast the next time. How did he become so good? And somebody said something here. What did you say it is? He said caching. Does everybody in this room understand the word caching? Yes, you do. That's why one rule in computer science, you never use words everybody understands. If they called it caching, you're like, cool, I know it. So they said, no, this is not caching. What is it then? This is even better. It's called memoization. So memoization. Hey, what is memoization? Caching. Okay? So the point really is, this technique is called memoization. He feels really cool. He memoized it, right? So what is memoization? So essentially you're saying, when you call this function, I'm not going to keep running it. I'm going to just return it. Do you want to see memoization in work? It'd be cool, right? I'm sorry, I can't show it to you. Because Java doesn't do it. But we don't have to see it in Java. Let's take a look. I'm going to go back here and say add AB equals A plus B. So I got a little function, an add function. Well, what is this code in? This code is in Haskell. There's a big difference between Haskell and Java. In Java, you remember what I said? The default is unsafe default. Java assumes everything will change. Haskell not only assumes, it makes sure everything doesn't change by default. In fact, in Haskell, if you want to change something, you got to beg and say, please, this one time, let me please change this variable. And Haskell will kind of give you all trouble and say, okay, only here. Right? In the case of Java, you have to say, please, please, one time I'll make this final. Right? It's a very complete opposite spectrum of the world. So in Haskell, almost everything is pure by default. So Haskell knows add is pure. Then I say main equals, and then you say do. What does do mean? I got a really nice name for do. It's called dubious operation. Right? Meaning you're doing something really funky. Well, you got to do these in Haskell. You got to define IO, meaning it's an impure operation. You got to ask permission to Haskell to do impurity. What impurity am I going to do here? I'm going to say over here print, and I'm going to say print add of 1, 2. So you can see in this case, I'm telling Haskell I want to do add of 1 and 2. It gives us a result of 3. But here comes the charm. Notice print is impure. Now, in the case of Java, I could get in and put a print statement and show you whether the code is being called or not, but I cannot do that in Haskell. Because in Haskell, if I put a print, it'll become impure. And the minute the code becomes impure, Haskell would not optimize it. So I was struggling with it. How do I prove that Haskell is doing memoization? And I never thought I would actually use debugger for this purpose. So notice what I'm going to do here. I'm going to go back here to Haskell, and I'm going to say, hey, Haskell. So I bring in the Haskell REPL, and I'm going to say in this case, hey, Haskell, load for me the sample.hs. So it loads the particular function, the file. Now I'm going to tell Haskell, hey, Haskell, put a breakpoint on line 1, character 16. That is line 1, character number 16. OK, great. I put a breakpoint there. Now I tell Haskell, go ahead and call main. Notice very carefully what Haskell is doing. Haskell is waiting on that function add. It's waiting on line 1 and characters 11 to 15, and Haskell is waiting for us. You say, hey, thanks, Haskell, for breaking over there. Please proceed, continue, and it says, sure, here's a result of 3 for you. But notice what I'm going to do now. I'm going to quietly tell Haskell, go run main again, and notice this time it didn't run it again. It immediately snapped back the result 3 to you, saying, hey, I've already run add, just like what he did, right? So it says, I've already evaluated this function before. I don't need to waste my time rerunning this. So this is the first time I actually came across this, which I was quite pleasantly surprised. I was playing with Haskell, and I called a function. That function would take a fairly long time to run, and it did, close to about 15 seconds to run. And 15 seconds later, Haskell said, blip, here is the result. I said, hey, that's cool, but I want to run it again. And I ran it again, and it immediately gave me a result back. I'm like, how did you do that? And that's when I discovered what Haskell is up to. It is memoizing automatically. And it says as long as the input is the same, the output is going to be the same. I don't have to rerun it. Now, in the case of Haskell, Haskell will make sure your functions are pure. But Java doesn't do that. And in fact, I think Java does something better. Java assumes your lambda expressions are pure. I like languages that assume. And the reason is, when a language gives you a compilation error, you will do stuff and say, yeah, the compiler worked, I'm happy. In the case of Java, you do stuff, and the compiler doesn't complain. And it just assumed that it's pure. What will happen if it assumes? Here's the question. If you and Java disagree, who do you think is going to win? Right? Java, of course. And the first time you do this, you get severely bitten. And the next, you limp for a few weeks, and you will never do this mistake again. That's why I like languages like Java, right? They just assume and say, I dare you to use it. And you're going to be very careful writing the code next time. So Java assumes lambdas are pure. So the moral of the story is, when you write a lambda expression in Java, you must make sure that it is pure. And remember what purity means. You don't change anything, but don't depend on anything that changes as well. Let me give you what that means as an example here in the case of Java. Now, in the case of Java, let's say for a minute I have a list on my hand. So I have a list of numbers 1 to 10. I want to loop through and print double of these values. So what am I going to do? I'm going to say numbers.for each, and I'm going to output in this case. And what am I interested in outputting at this time? I'm going to output e times factor. Well, let's say e times 2. You can see in this case, it prints all the values e times 2 it should. So in this case, I'm going to say, given an element e, print values e times 2. But I'm going to say, rather than 2, I'm going to say factor. Well, what in the world is factor? Factor is 2. And you can see in this case, it is using the factor. But what Java assumes is that factor actually is immutable, meaning you're not changing it. Now, what if you try to change the factor? Well, you would notice this real quick. You would say, in this case, to understand this, let's actually do it in 2 steps. I'm going to say .stream for a minute, and then I'm going to say .map. In this case, given a e times factor, and then I'm going to, let's say, do for each, and simply print the value out. So I'm going to say system dot, let's say system dot out, and I'm going to just say print line on this. So you can see the code still producing double of the values. Well, if I come here and say a factor equals 22, well, Java 8 says, well, you're not supposed to change a factor. I'm going to assume this is final. So this is called effectively final. So notice I get a compilation error saying you're not supposed to use factor here, because if you use a factor here, this lambda expression is no longer pure. You're seeing the reason why it's not pure anymore, right? Because the lambda doesn't change the factor. You are changing the factor outside. That's the condition number 2 I mentioned. You are not changing anything, but you're depending on something that is changing. That's a violation of purity as well. Well, good news, Java is protecting you right here. But unfortunately, Java doesn't go all the way through. Because sometimes programmers really say, oh, really, Java won't allow this, huh? Here's a really bright way to do this. And they would come back here and say, what if I were to say a square bracket factor equals new int, and then they're going to put this code like this. This is trouble waiting to happen. Because if you go back here and change it to a 0 right here, well, guess what's going to happen? Java doesn't complain anymore by changing this value. It says, I hope you know what you're doing, and it doesn't complain anymore, as you can see. So right now, at this time, this function is no longer pure. Why is it not pure? Because it is depending on a variable that is changing. This is bad idea. You should never do this. Okay, you should almost never do this. The only time you do this is if you hate everybody that you work with, right? Otherwise, never do this. So the reason why this is a terrible idea is you are mutating stuff within the function. What bad could happen? Let's think about what bad could happen in this case with a little example here. let's just do one step forward. Imagine we're not doing this. I'm going to go back to this code and say stream of integer, we'll call it stream equals, and I'm going to go ahead and save this into that variable of stream for a minute. And once I save into a stream, I'm going to simply say in here, a stream dot for each. Well, let's go ahead and bring in the stream on our hands. So I'm going to say dot stream dot star. And if I run this code, you can see the code is still doing the job. But here's what I'm going to do. I'm going to come in here and say a factor, the factor that we have on our hand, and then 0 equals 0. So this should be easy to even see what the output should be. But here's the question. The output is going to be double of the values, A, or the output is going to be all zeros. What do you think? You see that beauty? People are saying two different things. That's why this is such a bad idea. If you ever have to pause and think about it, that's a terrible thing to do. Because you don't want programs to become tricky like this. And in fact, very sadly though, it depends on when this function is evaluated. Well, this is the lazy evaluation. As a result, all the values are actually 0 in this case, and not the double of the value, because we did modify the value after the fact. That's a terrible, terrible thing to do. And that is one of the reasons why we should never mutate variables within which are being used by lambda expressions. So keep in mind the two definitions I gave. A pure function is a function that does not change anything, that does not depend on anything that changes as well. Both of those things are extremely important to keep in mind. So don't mutate stuff, make the functions pure, and we saw the benefits we get out of pure functions already. So what are the benefits we get out of pure functions? Well, functions are easier to test, they're idempotent, they are easier to understand, they can use referential transparency, and you can memorize it as well. So those are some of the benefits. But there is more benefits that you get out of it as well. We'll see some more benefits in a few minutes. So we talked about how we can benefit from pure functions, but what does it really mean? We don't mutate variables. Instead, what we do, we simply go through and transform objects and use it. Let's talk about this a little bit further. We want to see the difference between imperative style and declarative style. So let's understand what the difference between these two styles are, and then relate that back to the concept of functional style in a minute. So I'm going to write a function. The function I'm going to write here is called find Nemo, and I'm going to give names to it. And I want to know if our good friend Nemo is anywhere here. So I got a Nemo list over here of list of names, which includes Nemo in it. But I want to know if Nemo is in this list. How would I do that? Well, first thing I'm going to say is static void. Well, actually, in this case, let's make it a static function. So this is going to be find Nemo. I'm going to call a find Nemo function. List of string, we'll call it as names over here. And what am I going to do within this function? Well, the very first thing we'll do here is we will say, Boolean temp equals false. Then for string name coming from names, and what do we do? If name dot equals, and then you would say if the name is equal to Nemo, well, what do I want to do now? I'm going to say temp is equal to true, and then I would break out of it. Then what do we do next? We would say, in this case, if temp is true, then I would say found Nemo, so found Nemo. Otherwise, else, we will say, in this case, simply Nemo not found. So Nemo not found. Well, if I run the code, it says found Nemo. But look at this code for a minute. Anybody here who has written code like this before? Yeah, all of us, right? I know the reluctance. People are not raising hand like this. They're raising hand like this, right? Why? Because you're so ashamed. I feel your pain. I'm the same way too, right? It feels that way. Now, when you write a code like this, when you look at this, what are we doing? Well, look at this variable here. What are these variables called? Those are called flags. Anybody here likes using flags? No. We don't like flags at all. In fact, we hate them so much. We tell them, you don't deserve a good name. We'll call you temp, right? And so we give poor names to variables, right? And we don't like them at all. Then we loop through and do this. This is imperative style of code. And when you finish writing this code, you're not proud about it, right? You're not happy about it. But that's what we've been doing for a while. We've been writing code like this. But instead of all this effort, we can actually do something a little different. Notice what I'm going to do now. I'm going to take that away, and I'm going to simply say if names.contains Nemo, then go ahead and say found, otherwise not found. Well, look at that code for a second. We wrote all that code a minute ago. Instead, I just call the contains function. That is declarative style. So what's the difference? In imperative style, you take on all the effort. You say what to do, but you say how to do it as well. In declarative style, you simply say what to do. You don't spend your time saying how to do it. But I have a question for you. Look at this contains function. Can you tell me what this function is doing? It's the same as above you're saying. That's one answer. Any other answer? What else? It's almost the same? Okay, same, almost the same. Any other answer? It does, sorry? Do a search. Yes? There you go. That's exactly what I was looking for. He said, I don't care. How rude. Can you say it again in a more polite way? He says, it's encapsulated. That sounds so much better, isn't it? What does it mean? I don't care, right? So you don't say, I don't care. You say, it's encapsulated. Then we're all happy about it, right? I don't care. So the point is, it doesn't matter. So it doesn't matter in this context. We should get comfortable to let go and say, I don't care, right? Meaning, it doesn't matter to me in this context. I am more concerned about what this code does, not how it does it. If how it does it is a concern, I will address that separately, but I don't have to worry about it right now. So that's one of the very first things you do, is you go from telling me what to do and how to do, to simply telling me what to do, and let the underlying libraries take care of things for you. Now let's look at this a little bit further, how this will begin to feel. I want to take a collection. That's what we just did. I want to take a collection, but I want to double even values in the collection. So let's see how this is going to feel when we do this in Java, as we have been doing for a while. So let's go ahead and say, in this case, I have a list of numbers on my hand. And what I want to do is double the even values. How do I double the even values? First, you say list of integer doubled equals new array list empty. That's the very first thing you do, isn't it? And then you're going to print out the value doubled. Double of even, sorry, name this as double of even. And what do? Here's my double of even. But what are you going to do within this? You say for int element in numbers, and then you say if element is mod 2 is equal to 0 and, well, that's an even number. Then you say double of even dot add e times 2. So you are taking only even numbers, and you're finding the double of even numbers. Has anybody written code like this before? Yeah? You all have, right? So one brave person admitting in public, everybody else is like, they're just wiggling their little finger now, right? But I have a more important question to you. How do you feel when you write that code? Dirty, right? You feel dirty, he says this way. You feel really dirty. You go home in the evening, kids come running towards you, you say, don't touch me. I got to go shower first, right? It feels that way. It's even worse than that. Anybody works from home here? A few of us? Oh, there's a few of us. Be very careful. Because if you leave the computer on, and if a kid comes into the room and they look at it, they will come to you and say, that's what you do for a living? Right? And they never want to take after a profession after that, right? So this can be really dangerous. Well, this is an imperative style code. Well, for the sake of record, I grew up programming in imperative style. What that tells you is about my childhood. I had a terrible childhood, right? Because I've been programming in imperative style all my youth. Well, but we can do a lot better than this. Let's try this one more time. I'm going to come back here and say, in this case, well, before that, let's understand why this is not a great idea. Well, there are two smells of imperative code. The first smell of imperative code is you not only tell what to do, but you also tell how to do it. So notice, if you read this in English, how does it feel? Create an empty collection first. That itself drains your energy, right? In fact, it drains you so much that people start running away when they see the code like this, right? That feels that way, right? So it drains your energy. So you have this variable you're creating first, empty collection, you're defining it. Then you are saying, take one element at a time. Now then double the element. Stick that into this collection. If I turn up the volume and run this code, you will hear the variable double of even say, ouch, ouch, ouch on this line of code. That's the second thing, mutability, right? You're mutating it, and it's like sitting next to somebody who's just like, just stop, right? But that's what you're doing to this variable, constantly mutating it. Poor variable. Well, let's try this one more time. What I'm going to do here is I'm going to say numbers.stream, and then I'm going to say filter. And what am I interested? Given an element, element mod 2 is equal to 0 dot. And I'm going to say map given an element, element times 2 dot collect. And I'm going to say, in this case, to a list. So if you look at this code right now, what you have done in this case is you have nicely used more of a functional and declarative style. So collectors, I'm going to bring that in. Well, if you look at this code now, it produces the same output as the code in the top. But the one in the bottom is quite different in a couple of different ways. The first difference in the code in the bottom is, notice there is no mutability in this code. In fact, I've got some good news for you. In the code in the bottom, no variable was tortured in the making of the result in the bottom. It's a very humane code, right? That's what you're seeing here. The second thing in this code is you're telling what to do, not how to do it. Notice in the top code, you used a for loop. You probably have seen this before, right? So what do you do with the for loop? When you write code, just do a grep on your Java code and see how many times you have for in the code. You have for almost everywhere you see. Hey, I want to loop through all the values. What do you do? For. I want to loop through only a few values. What do you do? For with the if and a continue. I want to only loop through but get out of a few values. For, if, and break. Well, I want to skip some values and do some values. What do you do? For, if, break, and continue. Well, this for, how does it feel after a while? This feels like a hammer, isn't it? So you hear a knock on the door. You open the door. There's a guy standing there with the hammer. And you say, who are you? He says, I'm here to fix your kitchen. And you say, well, thanks for coming, but where are your tools? He takes a whack at the door and says, I don't need any stinking tool. I got this hammer. You probably will let the guy in and run out and call the cops because it's not safe to be in the house with the guy with the hammer, right? It feels that way. But on the other hand, that's a for hammer. But on the other hand, imagine you hear a knock on the door. You open the door. There's a guy with a little tool bag. You say, who are you? I'm here to fix the kitchen. Oh, come on in. And what does this person do? Lays the tools on the kitchen floor. And there's a hammer. There's a screwdriver. There's a chisel. There's a wrench. And you say, hey, that's all nice things. Oh, those are my tools. And you ask this person, interesting, are you going to use all of these tools? And the person laughs and says, no, I'm not going to use all of these tools because the person who uses all of these tools is called a consultant. Well, I'm going to use only tools that actually make sense, right, for the job on hand. So notice what you have here. A little filter tool, a little map tool, a little reduce or collect tool. Those are your little tools, and you put together whatever you want to do with these tools to make what you want to do, rather than that one hammer called a for hammer. So it's a very different way of thinking how we're going to write this code. So you can see how this is going to be building on these concepts. The second thing is, if you look at the code in the top, notice how we told what to do and how to do. In this case, we focus on only what to do. Let's try reading this code as against the other code. Well, the other code we read a few minutes ago, we said create an empty collection, start one element at a time. No. Let's see what we're doing here. Given the collection, get me only even numbers, double the values, and put them in a list. So notice how it flows through and gets the work done so easily. So that becomes a lot easier to work with. So given this, we looked at the imperative versus declarative, but that brings the question, what is the difference between declarative and functional? Well, declarative is where you say what to do rather than saying how to do. Functional is declarative. So in other words, anytime you program in functional style, you are also programming in declarative style. with one small difference. I'm going to say in this case, functional style is equal to declarative style plus higher order functions. So in other words, you are programming in functional style, then you automatically are programming in declarative style as well. So the only difference basically in this case is that a functional style is declarative style plus a higher order function. It's actually easy to see this in here. If you look at the function over here as a map function, notice what map is doing. It is a function that tells you that it's transforming, so it is declarative. But it also is receiving another function as a parameter, so that is functional style because it's higher order function. So functional style is going to be embracing the declarative style all the time, and then it's also going to have higher order functions in top of that that you're going to benefit from. So all the functions that you write in functional style also are really declarative in nature, plus you're using higher order functions to add on top of that. So given this, we focus on what instead of how. We don't mutate variables in this style. We write pure functions rather than functions with mutability in it. We pass objects, and we can also pass functions, and also we can use function composition. Well, we can go through a few more examples of this, but I want to get to some other interesting parts I wanted to really show. But if you really look at this, we already employed a function composition nicely right here. So notice how we went from a stream to filtering even numbers to doubling the values to collecting them or reducing them. That's a map reduce operation we performed. But when you're writing this code, notice the function composition. I often call this as a pipeline or a function pipeline. So you start with this function pipeline, and you go through the transformation from one to the next to the next to the next, and you keep flowing through to build your pipeline, and that is something you should get very comfortable with. So much like how in the imperative style, we engage mutability and the for loops and stuff like that, in this style, we're going to be engaging pipelines of operations more and more when we start doing this. But one benefit you get out of this is the code becomes a lot more easier to understand and easier to work with. It becomes easier to communicate what the code is doing, and as a result, it takes less energy to understand the code, less effort to understand the code. I was visiting a client recently, and they said, let me show you some Java code we have, which is doing functional style, and I don't know anything about their domain. So generally, I'll be really scared when somebody wants to show me code. But I sat down next to them, and they show me their code, and without telling me anything about their domain, it simply said, taking this collection of objects, I want to only extract these type of objects, and then do these to these objects, and then go further and select more objects. And I'm reading through the code, and I'm like, hey, I understand what this code is doing. And that's such a relief to be able to see what the code is doing and understand it. That's one of the biggest benefits you get out of functional style. So functional style is easier to understand compared to imperative style, which often is really hard to understand. So this leads to a few more things I want to really talk about here, which is about lambdas and closures. So what is the difference between lambdas and closures? Well, the first thing I want to say here is a lambda is just an anonymous function. So in other words, it's just a function. It doesn't have a name. It doesn't have any return types. It got parameter list, and it got a body of a function. So in this case, I can say numbers dot for each. And in this, I would say, for example, I want to output, let's say, double of the values. I could simply say, given an element, give me the element times 2. I want to return that value. So if I were to take this lambda expression right here, that's a lambda expression. But let's talk about this for a minute. If I ask you, what is 2? Well, 2 is very simple. It's a constant. There's no doubt in our mind what 2 is. But if I ask you what is e, well, we also know what e is. E is the parameter given to us into this lambda expression. So in other words, this lambda expression is like a well-fed baby. It's happy, it has everything it needs, and quietly taking a nap. So this lambda says, I've got 2 and e, I know what e is, I'm quite happy. Well, that's what a lambda is. A lambda is very self-contained. It's got everything it needs. On the other hand, if I were to say, in this case, numbers dot for each, and I'm going to say, in this case, e, and I'm going to output e times factor. Now, if you look at the lambda for a minute, I can ask you, what is e in this lambda? Well, that's very clear what e is. E is the parameter given to the lambda expression. But if I ask you, what is factor? Well, I'm sorry, I don't have a factor with me. In fact, this lambda is a little bit unhappy. It says, I don't have a part of me. It's missing. What is this factor? I don't know what it is. I got to bind to it. So in other words, this lambda has to go around and find where this factor is going to be. Well, in this case, this lambda has, the factor is currently unbounded, and the lambda, so the lambda needs to bind to this factor, right? To a variable which is a factor. Well, which is the factor, right? So where do we get that from? So for this, the lambda has to close over the defining scope. So in this case, it says, I'm going to walk over and find where this variable is. So if I define the factor right here in the code equals to 2, you can see that it's pretty happy with it. So this factor is in the defining scope of this lambda. So if you notice, what's the difference between a lambda and a closure? A lambda is self-contained. A closure has variables that it has to close over and bind. Well, try saying the word close over really, really quickly a lot of times. It begins to sound like closure. So a closure is nothing but close over. So a close over, this variable has to close over the defining context, and that's why it's called a closure. So what's the difference between a lambda and a closure? The difference is a lambda is self-contained. A closure has a variable outside the context of the lambda. It has to close over. Make no mistake, you don't want the outside variable to be a mutable variable. We talked about this a few minutes ago. So some people mistakenly say that a closure can have a variable that is mutable. That is wrong. We don't want mutable variables in closures. That will cause havoc to how we manipulate and manage lambda expressions. So the difference between a lambda and a closure is, a lambda simply is an expression. A closure is an expression that can carry a state from one location to another location. So this gives a way for us to transport state, but it better be immutable state. Why? Because we all know mutable state is evil. And so you don't want to carry a mutable state with you. It's got to be an immutable state. That's something to keep in mind when it comes to having these variables. So we talked about what a closure is, but how does this really help us to get moving? Well, we need to rethink about the way we do things. And for this, I want to talk a little bit about lazy evaluation first, and then I want to talk about how we can take that further into something much more wonderful. So I want to talk about 2 more examples here, at least, to get a feel for it. Let's say in this example, I want to take this particular collection of values, and I want to perform a lazy evaluation. So what does it mean to be doing a lazy evaluation? What does that really bias? Well, lazy evaluation says, I'm going to postpone evaluating until I no longer can postpone it. That's what lazy evaluation really means. So we already saw an example of this. Let's look at one more time. I'm going to say stream, in this case, integer stream equals, and I'm going to say numbers.stream, and I'm going to say, in this case, a filter, and given a number e, tell me if the number is an even number. Well, in this case, of course, then I'm going to say dot map, given a value e times factor, and now I have a stream on my hand. Now I'm going to say output, let's print, and now I'm going to say, in this case, output stream dot for each, and I'm going to say system dot out and print line. So in this case, you can see that I am going to print the values. What is factor? Factor equals, let's say, 2. And you can clearly see, let's print, and it printed the twice of the values for even numbers. But the question is, when did it evaluate the values in here? When did that computation take place? That's called the lazy evaluation. And the benefit of lazy evaluation is you're not going to perform anything until the last responsible moment. Meaning, I will avoid doing it as much as I can, and only when I cannot avoid it, I'm going to really do this work. That's what we're going to do, right? So you're going to postpone until the last responsible moment. So how do we go about doing that? Well, let's take a look at how this actually works. I'm going to change this to a sample double value. And in this case, I'm going to go ahead and write this function. Let's go ahead and say this is a static int double value. Given a number, I'm going to say return number times, let's say, 2. Well, in this case, you can see it still produces the value. Now, had I put a breakpoint here, I would have seen this. But I'm going to do something that's not a good thing. I'm going to say called over here. Generally, you don't want side effects like this, but just illustrates the point. But notice where the called is coming through. You can see in this case, we called the map first. Then we are calling this function right here, which is let's print. And then we are calling the for each. But did you notice the output? It first said let's print. And then it is doing the call. So what does that tell you? It tells you that the call to map did not execute until you came down to the for each statement. In fact, if you want to really see this a little further, notice that I'm going to comment out only the for each right now. And when I run this code, you can see all it does is it simply says let's print, but it never actually runs the other piece of code. The map function never got executed. And the reason for that is map is absolutely lazy. So lazy evaluation is something very powerful. So what does lazy evaluation say? Lazy evaluation says, I'm going to postpone until the very last responsible moment. If I can escape and don't do this at all, I would rather not do this. Imagine for a minute, your boss calls you and says, I want you to work, let's say this is 1st of February, and your boss says, I want you to work on this project, and I want a report from you on the 1st of April. Now, that's a great day for any report, and what are you going to say? You're going to say, absolutely, I'll be thrilled. And you will very promptly start working on this report and the project on March 31st, isn't it? Because why would you want to do this before, March 31st when it's due on April 1st? In fact, if you know something your boss doesn't know, your boss expects a report on April 1st, but you know you're going to quit on March 15th, why would you even bother starting this report any sooner, right? Well, in this case, of course, you would postpone until the last responsible moment. But there are some bosses who are very boring bosses, like I do sometimes, and that is your boss says, I want you to work on this. The final report is due on April the 1st, but you are going to create a report, an interim report, every Friday. That job sucks, isn't it? Because you got to do some work, at least pretend to do some work every week, so you can give a report on Friday. So in other words, what is necessary for lazy evaluation? You cannot be lazy if your function has what? Thank you. That's correct. So in other words, we just said, if you don't have a side effect, you can be lazy. That's why printing an output is a bad idea, because you get to know what this function is doing. So notice how this really becomes a lot better now by the fact that you can be lazy. By the fact that you can be having no side effect, suddenly you can be lazy now. So what appeared to be a stupid idea in the beginning, where we said no mutability, you can quickly see the power of no mutability all of a sudden. If you don't put mutability in your code, it gives you all that benefit. But that's not enough. There is one other bigger benefit we can go to, and let's take a look at that next. So what am I going to do next? I want to go a step further with this. I'm going to look at what we can do here. I want to find a number if a number is a prime number. Let's start with that first. So what am I going to do? I want to know if a number is a prime. So how would I do this? Well, let's start with this question first. I'm going to say output is prime of, let's say, 1. But I'm going to ask for a few more. Let's say 2, 3, and a few more, like a 4, a 5, a 6, and maybe one more, a 7. Well, we know which of these are prime, which of these are not, but how would we go about doing this? Well, let's say in this case, public static Boolean is prime, and then I would say, given a number, what am I going to do here? Well, let's start with this. I will first of all say Boolean divisible is equal to false. Then I will say for int element, well, in this case, for I equal to 2, I less than number, I plus plus, and what am I going to do? I'm going to say here if the element, the number mod I is equal to 0, then I say divisible is equal to true and break out, and then return number is greater than 1 and not divisible. Well, run the code and see. It says 1 is not prime, 2 and 3 are, 4 is not, 5 is, 6 is not, 7 is. It works. But look at the code we just wrote. Now, in this code, this is a clearly imperative style. We all have written code like this. And you remember what this variable is called? It's called a flag. And I mentioned that nobody likes flag. In fact, that's one of the reasons why I even misspell it, because it doesn't deserve to be there, right? We all hate it. So this is an example of a flag we are using, but this is an imperative style. Let's rewrite this in functional style. So I'm going to say, in this case, return number is greater than 1 and int stream dot range from 2 to the number. And I'm going to say, in this case, none match, given a value at index, number mod I is equal to 0. So if you notice here, we got the same result out of the code, but it's a lot less code. But it's not only a lot less code, it's a functional style code. We convey what we want, not how to do it. It begins to read like the problem statement. It becomes a lot easier to work with, as you can see. So that is one example of how we can make the code a lot more easier to understand, easier to work with as well. That becomes a lot powerful way of communicating our intent. Well, that's great so far, but I want to go a step further and implement one other feature right here. Now, while immutability and pure functions are really part of functional programming, so when you read about functional programming, what do most books try to tell us? What do most people try to tell us? They tell us, oh, you got to program with immutability, you're going to program with higher order functions. Are they correct? They're absolutely correct. However, those things don't excite me, because I usually ask the question, why? Why should I care about immutability? Why should I care about higher order functions? Well, the reason is those are really stepping stones or pathway to a beautiful place, a much better place than we can be. And that is, at the very heart of functional programming, what we really have is function composition and lazy evaluation. So we do all of this so we can be lazy. And both in life and in programming, it's a good thing to be lazy, right? So anytime you are really, really eager to do stuff and you do all the things really ahead, what happens? It becomes a waste. You want to really delay it until the last responsible moment and do things, because then you can just be focusing on the minimum operation. Okay, maybe not so much in life, but certainly in programming, it becomes really more efficient to be lazy. So how can we really benefit from that? We already saw the function composition already, but I'm going to employ that into lazy evaluation. So let's see what we can do. Find the first prime number greater than 100, where its square root is greater than 20. Well, let's give it a try, how this is going to play out. And then we will see how we're going to implement this code in imperative style, and then we'll do this in more of a functional style. So find the first prime number. So we got one prime number. Greater than 100. Okay, so the minimum value is going to be 100, where its square root is greater than 20. Okay, let's start with that first. So we can say index equal to 100. Well, it says greater than 100, so that better be 101. Great, that's the first value. Then what am I going to do? I'm going to say while, well, let's say true for a minute. And I'm going to say if E is prime, so we'll say E is prime of index. Well, if that is true, what should I do? Well, it says the first prime is greater than 100. It's a prime number. Its square root is greater than 20. Oh, we're not done. And math.square root of the index is, of course, greater than 20. That's the next thing we want. If it is true, what do we want to do? We got the number, break out. Well, if it is not true, what do we do? Index plus plus, obviously, because we want to keep going, right? So in this case, we're going to say, we're going to take the value 101, and while true, if index is prime and math.square is greater than 20, break out. Otherwise, keep incrementing the index and keep going. Well, when we are done with it, what's the next thing we're going to do? We're going to come down here and say output. Well, find the first number greater than 100. Where it's square root? Well, all I'm after is index. I want to print the value of index. Well, it printed 401. Well, we could argue the code is not very complex. Well, but actually it is, because we had to do very low-level operations. We had to set a variable here. We had to then increment it. We had to check for conditions. A lot of little things we had to do. Well, can we do better than this? We can do a lot better than this. Let's see how we're going to do this now. So rather than doing this operation, what I'm going to do here, let's try this one more time. I'm going to first of all start with a stream.iterate. And this says, starting with a 101, given an element plus 1. So if you notice in this case, this is an infinite stream. So this says, I'm going to start with the value 101, but I'm going to ask for the next value, the next value, the next value. So 101, 102, 103, 104, 105, keep going like that. Now you may look at this and say, how far do we go with this? Well, there comes the beauty. This doesn't do any work. It's a lazy evaluation. So in other words, when you call this particular code, it doesn't do this job at all. It simply says, yeah, some other time. I don't have to do this right now. So it completely postpones evaluating this particular operation. In fact, let's actually take a look at it to make sure it is doing that. So I'm going to say sample, and I'm going to say increment. After all, I'm just trying to increment the value. So public static int increment. And what am I going to do? Given a number, I want to return, in this case, return number plus 1. So when I run this code, you can see it produced 401. If I output here inc, you can see that it never actually called the increment. Why? Because that's absolutely lazy. So it says, I don't need to really run increment. And why not? Because you never made use of the result. Why should I run it right now? So that's how lazy it is. I'm going to remove the print statement now. We already saw the laziness right now. Well, that's great so far. What am I going to do next? Well, now that I have an infinite stream, I'm going to come to this infinite stream and say filter sample is prime. So what does this do? This says, go ahead and call for all the values which are from 101. That's an infinite stream. But I only want an infinite stream of prime numbers, not all the numbers. So both of them are infinite in size. The first one is infinite. The second one is infinite. But there is also another thing very common between the two. They both are also lazy. They don't do any work at all, right? So they both kind of say, we don't have to do any work right now. Well, then what am I going to do? I'm going to say filter, and I'm going to take a value, and I'm going to say math.square root of the value. And what am I going to do with the square root? Well, the square root of this element, e, is greater than 20. So now I'm saying, don't get me all the values, all the primes. Only get me the primes whose square root is greater than 20. That is also infinite in size. So you went from an infinite series to infinite series, a prime to infinite series of primes greater than square root of primes greater than 20. Then you are going to say dot find first. You're asking, just give me the first value. Thank you. So in this case, I got the first value, and I'm going to call a get on it. Generally, it's a good idea to check the value before you call get on it, but I'm going to ignore that for a minute, and I'm going to just print the value. Now, let's take a look at what we just did. We said, given the values, get me all the prime numbers, get me only the prime numbers whose square root is greater than 20, but get me the very first one. Now, keep in mind, these are all lazy evaluations. And the only thing that triggers this computation is the find first. And the minute you trigger the computation with the find first, it says, I am going to do only enough work to get you that one value, and as soon as you got that value, I'm shutting the door and going home. So as a result, it doesn't waste its effort doing a lot of work. It does work minimally to get the result. So of course, when I run this code now, you can see in this particular case, it's going to get the result for us. The original one said 401. Well, the second one is telling us 401 as well. But you can see how the code is structured very differently in this case. And what are we doing here? We're using infinite series. Well, what we just did is, if you have a lazy evaluation, this can do quite a few things. This can also lead to one other benefit, which is infinite streams. Now, what does infinite streams do? Infinite streams give us another tool on our hand. And we can start designing applications where we can think of infinite series to work with. So in other words, when you look at this here, we said you can start with a lazy evaluation, but you can then start employing an infinite streams of operation, and you can see how that changes the way we're going to do things. So this tells us you can start modeling your applications as an infinite series problem. Well, what kind of problems can fit into this? Well, it's our creativity that is going to be the limit of this. I was working with a problem when I was writing the Java 8 book, and I wanted to really show how to do tail call optimization. And I struggled with it for a couple of days. And I wasted 2 days of my life trying to show how to do tail call optimization. And when I finished writing the code was utterly ugly. And I looked at this code and said, oh my gosh, this is really poor. And I struggled with it. I had mutability in code. I had while loops in code. I had everything that I told people not to do. And so this code really absolutely sucked. And I struggled with it for about 2 days. And I looked at this code, and I have a while loop with a variable being mutated. And I was struggling with this, and I said, if I write this code in the book, people are going to look at this code, and they're going to laugh. Because until the previous page in the book, I told people, don't use for, don't use while, don't mutate. And what am I doing in this page? Using while, using a mutation. And I struggled with it for about a day, and I came with what I thought was a brilliant solution. And my brilliant solution was to just write a paragraph. And the paragraph was going to say, dear reader, do you see me using mutability and while loop? I leave it as an exercise to the reader to transform this code to avoid this. Usually, which means your author has no clue. And I thought, that's very cheesy. I shouldn't do that. Then I came up with a second solution, which also was a brilliant solution. My second solution was, dear reader, do you see me use mutability in this code? And do you see me using a while loop? I recommend you don't do that except cases like this where you can avoid it, which also means your author has no clue. And I realized my code absolutely sucks. So I left it alone, and I kind of went away. I said, let me think of something else. I got to move on. Well, a few days went by. I was on the treadmill jogging. And of course, I'm away from the code. I'm away from the computer. A few days of not working on this. But in the back of my mind, a little thread is thinking about this problem, how it sucks, and what can I do? And it suddenly dawned on me, oh my gosh, I can think of a tail call optimization as an infinite series problem. Well, every tail call function can be visualized like it's an object, and I can have one tail call calling the next tail call, calling the next tail call, until the last one, which says, I don't have any more call to do. And suddenly I realized, oh wait, this could be an infinite series problem. I jumped out of my treadmill, ran across my house while my children screaming, are you okay, Daddy? I'm like, I think I have a solution. 15 minutes later, I transformed the code into a tail call optimization. And within about 4 or 5 lines of code, I had a sweet little tail call optimization working. And finally, I was able to actually put that in the book as well. So the point really is that you can actually write this code in a very effective manner to make this really optimal. So given this, we don't want to really do the infinite immutability because it's a fashionable thing. So we started out by saying immutability is a cool thing in functional programming. But why? Because immutability gives the ability for us to write pure functions. Well, pure functions are cool. Why? Because we can do so many things with it, including lazy evaluation. Well, lazy evaluation is cool. Why? Because we could do infinite streams. But you can see all these building blocks now we have with functional programming. So immutability is not something we do because it's fashionable. It's what we do because it leads us to a greater good, and those are the expressive power we get out of the language. So not only is the code easier to understand, easier to express, easier to write, has fewer errors in it, it also becomes easy to parallelize the code and also to be able to use lazy evaluation and infinite series as well. Those are some of the benefits that functional programming leads us towards. So very powerful approach, as you can see here. So with Java and many other languages providing this kind of capability, there is really nothing that stops us from using it. And of course, it's going to take effort for us to start using it. It's something we have to do to change the way we think about problems and solve it. But when we get a hold of how to really think in this way, I think we got a lot of fun ahead of us. I hope you found that useful. Thank you.